Have you ever thought, man, being a TA would be cool? Or, man, I really like 1332. Or, Jacob's such a cool guy. I wish I could be more like him. Well, in that case, do I have news for you? The TA application is now open and available at ta-app.cc.godtech.edu. Apply to be a TA for 1332 today. Offer will be contingent on interview. See Canvas announcement for requirements and eligibility. Hey everyone, welcome to Recitation. As I just mentioned, the TA application is now open now for all students. We sent an announcement about that earlier today. We talked about it a bit in a lecture last week. Definitely apply if you think it sounds like something that you would be interested in doing. Personally, this has been one of the most enjoyable things I've done. I love being a TA and I love doing this. Wouldn't give it up for the world. Kind of have to give it up when I graduate, obviously, but never give it up in my heart. So definitely, if you've gotten helped out by TAs this semester, if you've enjoyed some of the stuff in Recitation, thank you, Anonymous. If you've enjoyed some of the stuff in Recitation and you think that being a TA sounds like something you'd be interested, apply. There are some requirements associated with like what other things you can be doing at the time. The big things is you can't have like another on-campus job for something. But you can see that slide deck we posted for more information, and I mentioned in like one of the Piazza answers that you can email Dr. Monica Sweat for more information about like requirements if you have like super specific questions that you don't think apply to the slide deck. Do you have a limited version of Jacob for Halloween? I don't have anything good for that, unfortunately. I can't think of anything. Maybe if I come up with something, you'll get something fancy. Regardless, today will be a bit of a shorter recitation, hopefully. What's kind of happened is you've probably noticed that recitations have started to get a decent bit ahead of the lectures, which isn't really the point of recitation. It's supposed to be a recitation of the material. And I know this doesn't even really apply to some students in the online section or students that don't really watch the lectures as much or watch them asynchronously, but we still don't want to be too far ahead because as it stands, we would be done teaching new content with like a recitation and a half left over, which is a lot, even just to do like final review stuff in. So we're trying to tone it back a bit. Plus, I think you guys will appreciate some sorting review, which is a lot of what today's going to be. We will be covering some new content today, but just as a warning, a lot of today's recitation is going to be stuff we talked about last week, just recapping it and kind of presenting it in a more concise way. With that said, let's go ahead and get started. Your usual announcements you have a homework that you're working on right now. You've had it out for a while. It's your sorting homework that is due on this Friday, the 30th at 11:55 p.m. with the 2-hour grace period. If you haven't started on that, and you should definitely start as soon as you can, especially after this week's recitation, because we'll be covering all the sorts again. Try not to do it last minute. It's not that it's too difficult to do last minute, it just can be kind of long, and if you start it last minute, you'll run into some potential time issues. Give it a couple days just to make sure you get it done, get it tested. There's a good chance that if you're passing all the student J units on this one, like the ones made by students, that you're in a pretty good shape. These algorithms homeworks tend to be much higher average grades compared to the other homeworks. So while this course can be a little bit backloaded in terms of like grades and exam related stuff, the actual difficulty of the homeworks tends to scale down a little bit. Speaking of that, homework 9, that's pattern matching homework, which we're going to start talking about today, will release on that same day. It's a 1-week homework due on the 6th. Next week, we'll be covering the algorithms that you're dealing in that one, but we're at least going to introduce the concept today. You've got a recitation worksheet that you can find on Canvas, same place it always is. Today, as I mentioned earlier, we're going to be doing a review of the sorting algorithms that we've talked about, and an introduction to what pattern matching is, and kind of the most simple pattern matching algorithm that you can have, which is the brute force algorithm. With that said, let's go ahead and get started with some of the iterative sorts, or sometimes we call them the n-squared sorts. For a lot of these, I'm going to try to give you guys some time, especially at the beginning and end, to like take a picture of these, because you probably already have a lot of this stuff written in your notes. I don't think it's anything other than some stuff you'll see later. I don't think it's anything new that wasn't on my notes last week. So I don't know if rewriting everything down will be beneficial to you, but obviously that's going to be dependent on each student. So with that said, let's go ahead and start with bubble sort. Remember that how bubble sort works is we repeatedly are swapping kind of adjacent out of order elements through the array, which in turn will end up bubbling the largest element up to its proper location. So it'll bubble the largest element to the end, then the second largest to the second, to the last position, so on and so forth. This is kind of like the most basic sorting algorithm. If you had never heard of any sorting algorithms before, and someone told you, code a sorting algorithm, this is probably the one most people would kind of inherently do. At least this was the one I did, because you're just looking at adjacent elements and checking whether they're in order or not. And anytime things are out of order, you switch them, and eventually you stop switching things, and that's the end, and then your array is sorted. So it's super simple, and a lot of people learn it outside of this class. Remember, we do have that extra optimization, though, that we can remember the location of our last swap. So we don't care about the first swap, we care about the last swap, specifically the kind of right side of that last swap, and we say that all of our future bubbling can swap there, because if we ever stopped doing swaps at some point, we're not going to have to do any kind of switching around after that point. So that's a nice thing that can prevent us from doing a ton of extra comparisons. And you'll also note that because of this optimization, if we ever don't do swaps over one entire iteration, that means our array is in order, so we don't have anything out of order, so that means we can terminate instantly. So that means if we pass in a sorted array, it will do one pass over the array, not do any swaps, and stop instantly, which is super cool. Our efficiencies, remember we have that best case O of n for a sorted array, where you do one iteration and stop. That worst case n squared for a reverse sorted array, where you have to bubble all the elements one by one. Average ends up being n squared too, because bubble sort isn't very good, and these iterative sorts do a ton of comparisons. We've got an in-place algorithm, because we don't need to create any data structures. It's stable, we always do these kind of adjacent comparisons, we never do any long swaps. And it is adaptable, because if our array is sorted or nearly sorted, we can take advantage of that. Now, from bubble sort, someone said, okay, bubble sort is good at doing almost sorted arrays, or arrays where we've got the largest element at the beginning, and but something bubble sort's really bad at is where we have the smallest element at the end. So someone said, okay, cool, maybe do bubble sort backwards then. But then bubble sort backwards has issues with large elements at the beginning, so some genius said just do both. And then we got cocktail shaker sort, where we alternate between one forward iteration of bubble sort and one backwards iteration of bubble sort. So we do one set of forward comparisons and swaps, and then we start going this way and swapping things down. So every iteration, remember, one iteration of cocktail shaker sort is the combined forward and backward iteration. So overall, compared to like bubble sort, we do twice as much work per iteration, but half as many iterations. So after each iteration, we've put the largest element to the end of the array and the smallest element to the beginning, and we kind of keep building our fixed portions down inward towards the middle until we've sorted everything. And with this optimization, how it changes from bubble sort is now, instead of just keeping a record of the last swap in one direction, in both directions we keep track of a last swap. Now notice this is still a last swapped optimization in both directions. When we're going to the right, we keep track of the last swap, and when we go to the left, we keep track of the last swap. At no point do we need to remember the first swap we do, only the last one. That's where our optimization comes in, and that allows us to kind of cut in our completed sections faster than just one element at a time. Our efficiencies are the same as bubble sort. We still have issues with like reverse sorted arrays, and we're still able to instantly terminate with, or not instantly, but after one pass terminate with a completely sorted array, and we don't do asymptotically better on average. We don't have a better average big O, and it's still an in-place, stable, and adaptable algorithm for all the exact same reasons as bubble sort. Insertion sort's up next. This is an idea where we divided our array into two parts. So we took our whole array and we said, okay, this is going to be the sorted section of our array. This is going to be the unsorted section of our array. So we start with one element in the sorted part. What we do is we keep taking elements from the unsorted part, placing them in the sorted part in their correct position, which expands that, and just one by one inserting elements until until our sorted portion is now the entire array and there's nothing left unsorted. Remember, how we do that inserting algorithm is we take it and we kind of bubble it down one spot by one, swapping it until we find a spot where it no longer needs to do any swaps. And that little optimization, I say optimization, but it's really a part of the algorithm, is if we ever don't do a swap in the process of bubbling it down, we don't need to do any more comparisons that iteration. We stop and move on to the next element. The good analogy I always like to give to this is it's like if you have a hand of playing cards in some card game, and you like to keep your cards in sorted order because you're playing like Rummy or something, and having your cards sorted makes it a little easier to keep track of what you have. You have your cards in sorted order, that represents the sorted portion of the array, and like the deck that you're drawing cards from represents the unsorted section. So you draw the cards one at a time, insert them in their correct spot, then draw a new card, insert that in its correct spot, and you do that until your hand is filled up. So it's a really similar algorithm, and I think that analogy has always helped me, even like before I got into card tricks and stuff, so I think it's a useful analogy. Unsurprisingly, all of these big O's and properties are the same as the other algorithms. Best case O of n for when we have a sorted array, worst case n squared for a reverse sorted array, on average still n squared, in place, stable, adaptable, nothing about that should be too surprising. Give people a little bit more if they want to take a picture or finish writing stuff down, then we'll talk about the last n squared sort in selection sort. Hopefully that's enough time. Let's move on to selection sort. Selection sort, also known by many people as the bad sort. How this one works is we select the smallest or largest element that we have not yet put in its correct position, so something that we haven't selected yet, and we swap it directly to its correct position. So every iteration of selection sort is going to select one element and put that one element in its correct position. So once we've done that for every single element in our array, we're done and our array is sorted. Remember that for smallest elements, that means we're swapping them to the front of the array, front kind of like moving forward every single time we do a swap. Largest element is the back of the array. Both methods, smallest or largest, do the exact same number of comparisons and swaps, so you don't need to worry about like which one you did. When we give this on a homework, students are allowed to pick either, but I believe this one isn't on your homework this semester. In general, selection sort performs much fewer swaps than a lot of the other sorts, because you at maximum do n swaps, or at maximum you do n-1 swaps, assuming that elements never swap with themselves or anything, which is usually going to be a lot less than any other algorithm. I hesitate to say always less than any other algorithm, but I think it might be bounded by that. Either way, if you're in a situation where writing to memory is expensive, selection sort could be really nice because you do few swaps, even though you do a ton of comparisons. You'll remember that this is an algorithm that's O of n squared always, because the algorithm is completely independent of what is currently in our array or the relations between elements, which is why we have a not adaptable sort. Still in place though, because we're not creating any other data structures. And remember, it's unstable because we do those long range swaps. We're not just swapping things that are next to each other or something like that. So we lose that stability. We lose the stability, we lose the adaptability, we lose a best case of O of n, but we gain that few number of swaps, which is good occasionally. And selection sort is a very simple sort, which can be nice for some applications. Someone asked a great question that I kind of want to mention too. Could you optimize selection sort by selecting the one largest and one smallest in each pass-through? You could. You're going to be doing twice as many comparisons per iteration, but you'll cut your iterations in half. So overall, kind of same amount of work. It's kind of like what we do in cocktail shaker sort, but it's not going to be significantly better. A little bit longer on this, then we'll start moving on to the more complicated sorts, starting with the divide and conquer ones with merge sort. We'll try to get through those. There's only 3 of them, so. Alright, hopefully that should be good for selection sort. Now let's on to merge sort. This is the only one where I actually have new things on this page. It's not new things that you need to know, but it's something I didn't talk about last time that I wanted to mention. That's this big section down here. I'll get there. Remember how merge sort works is merge sort says I'm too lazy to sort anything. I'm scared of sorting algorithms. I don't want to sort anything larger than a size 1 array, because size 1 arrays are easy to sort because they're already sorted. So all we do is we continuously split our arrays in half. We recursively sort both sides, and then we merge them back together with this merge algorithm that we talked about. Remembering that, again, size 1 arrays are always sorted, so once we get down to size 1 base cases, that's when we can start going back up. There is actually termination there. The algorithm overview as a whole, we split and copy into both subarrays, merge sort both subarrays, which is going to involve more recursive splitting and copying, but at the end of it, both of our arrays should be sorted, and then we merge them back together in the original array. And remember that merge algorithm was us. We compared the 2 elements on the far left. Whichever one was less went back into our original array. Then we kind of shifted this pointer forward by 1, compared them again. Let's say this one's less again. Goes back into our original array. We shift over. So on and so forth. We keep comparing the leftmost elements in both subarrays, putting the smaller one back into our original array, and then kind of moving that forward by 1. Once one of those subarrays empties, we just kind of copy the rest of the subarray back into our original array without doing any extra comparisons. Also keep in mind that if the elements are equal, we always take the one from the left subarray. That's how we get our stability, because that's when we have duplicate elements, we always want the one that was on the left, I mean the one that was originally in front, to remain to the left or in front of the other one. So that's how we maintain this stability in merge sort. Even though it feels like we're not comparing adjacent elements, we still maintain that. It is an out-of-place algorithm, though, because we have to create these new subarrays, and it is not adaptable because nothing about this takes advantage of pre-sortedness. The efficiency is what I want to talk about. Someone asked about size 2 base cases. So size 2 base cases should work also. I don't like doing them on merge sort specifically because I think it kind of ruins the whole elegantness of never actually sorting any elements on its own. But that should not cause you to fail any tests on your own. That likely means you're missing something else. Make sure that when you're splitting odd length arrays, you're putting the extra piece of data on the right and not the left. That's a common mistake. So efficiency, I told you guys last week that the efficiency of merge sort is n log n, but I didn't really tell you why. I'm going to get into that a little bit right now. So originally we have this length, there's a lot written here, I'll try to get through it. Originally we have this length n array, and remember what we do is we split it into 2 length n over 2 arrays and call sort on both. Then those are going to result in splitting into length n over 4 arrays, so on and so forth until we get down to length 1. So if we look at the amount of levels we have here, you'll recall that this is really similar to other recursive stuff we've talked about, that this is O of log n when we split like this for this height, because it's exactly the same as like a balanced binary search tree or an AVL, where it's the number of times you divide by 2 to get down to 1. That's log base 2 of n. So we have log n levels here. So let's see how much work are we doing on each of those levels. So the splitting work takes some time, but the real work I'm going to focus on here is the merging part, because that's like the real work that merge sort's doing. When we're merging these two subarrays, these two length n over 2 subarrays back into our original array, that takes total O of n time, because we need to overall look at every single element in both of these subarrays, which is O of n time. Now on this level, this subarray, the merge back into it takes n over 2 time, because we have to place every single element in this length n over 2 subarray. And we have to do that same amount of work here, so it's going to take n over 2 time to put all the work into this subarray. So the total amount of work done by the merging on this level of the subarray is n over 2 plus n over 2, which is n. And on this level, we're going to have to do n over 4 work for this, for this, for this, for this. So we've got n over 4 per each of these 4 arrays, which is also O of n. So we have that each level of this kind of division takes a total of O of n time combined across all the subarrays, and we have O of log n levels. So we get n times log n, which is where we get this n log n. And that's where the work comes from. Now, a common misconception that comes from this diagram is people assume that we also have n log n space, but a cool thing about merge sort is we don't actually need to create all of these arrays at the same time. You'll notice we split this into 2 length n over 2 arrays, but then we only are going to sort this one first. So we don't create these 2 arrays at all yet until we finish this one. Then when these 2 n over 4 arrays are created, we're only going to call it on this first n over 4 array. So we kind of get this diagonal grouping of arrays instead of this whole block. And if you sum all of that up, then you get n plus n over 2 plus n over 4, so on and so forth, which ends up being total O of 2n, which is O of n space. And that's not important for this class. You don't need to know that. But that is useful, and that's a common misconception that people think merge sort takes n log n space, when in actuality, it's just n log n time O of n space. Give a little bit longer on this, then we'll move on to LSD Radix Sort. All right. Up next is going to be LSD Radix Sort. Just as a reminder, if you're struggling with LSD Radix Sort, take a look at Reality Check 30. It's got some useful tips and code for you that you'll probably find. How Radix Sort works, though, is the first thing we do is we sort by the ones place, then we sort by the tens place, then we sort by the hundreds place, so on and so forth. And the cool thing is we do each of these sorts in a stable manner. What that means is after we've sorted by the hundreds place, if numbers have the same value in the hundreds place, they are relatively ordered by sorting them by the tens place. And if numbers have the same hundreds and tens place, then those two numbers are relatively sorted by their ones place. And that keeps applying further and further up. But the cool thing about this is it looks like completely unsorted throughout all of these early iterations until this last iteration just magically sorts everything. So a lot of people, when they see Radix Sort for the first time, it just looks like some crazy black magic went on and the array magically sorted itself. And you are not alone if you feel that. That was how I felt when I saw Radix Sort for the first time. I had no idea what was going on. I was so confused, like, didn't feel like the array was getting sorted at all, and bam, magically everything's in its order somehow. So it definitely takes some time to get used to and figure out exactly what's going on. How the algorithm works, though, is this first step, and this is, if you've done the reality check, you'll note that this first step is actually optional, but it is a very common way to do it, and it's kind of the basic form of the algorithm. We're going to determine the total number of iterations, which we often call k, by finding the longest number, and then getting that number's length. So k equals the length of this. So we find that longest number. Remember, that's the number with the largest absolute value. Find the length of that. Remember, we can do that by dividing by 10 until we hit 0. And that gives us k, which is the total number of iterations of Radix Sort we need to do. Remember, there's some tricky stuff with integer.min value for this. There's some great answers on Piazza, I believe, explaining exactly what goes on with that. You'll need to remember to be careful of that. Also, if you do reality check 30, there's ways to avoid this. That's fine too. Both implementations are valid. Then we're going to create 19 buckets. Remember, those buckets are for all of the digits, including negatives. So -9, -8, -7, -6, all the way up down to 0, or up to 0, then 1, 2, 3, all the way through 9. That's 19 total, because 9 negative, 9 positive, and 0. And that we generally have as an array of linked lists. So it can be a couple other things, but array of linked lists is the most common thing and the easiest to use. Then how it works is on each iteration I, we go through each number and determine what digit is in the ith place. So on the very first iteration, that's the ones place. On the second iteration, that's the tens place, so on and so forth. How we do that is we take our number, we divide it by 10 raised to the ith power, we mod the result of that by 10, and then we add 9. I know people were confused because I didn't have like the order of operations as clearly written on here before, so I tried to be more explicit with that this time. But exponentiation, then division, then modulus, then addition. It turns out that that's the order of operations anyway, so some of these parentheses aren't needed, but it makes it a little clearer, and I apologize for that last time. As an important thing, remember this 10 to the I should not be calculated with any form of power exponent method. Math.pow is a forbidden statement. Don't use it. Don't write your own power method. Don't write your own exponent method. You'll be doing this with a kind of running divisor, where it's a value that you keep multiplying by 10 at the end of each loop, because you only need one power of 10 for each for each iteration of Radix Sort. If you're confused about how to do that, take a look at Reality Check 30. It's got some code that you'll find helpful. This is going to give us an index between 0 and 18. And that's going to be what bucket we're supposed to add our number to. So if this gives us, if we get that, this gives us the actual like digit, so this gives us a number between -9 and 9. And by adding 9 to that, we get a number between 0 and 18, which is an index into our size 19 buckets array. So that's the bucket we're going to add to. We'll do that for every single element, which is filling our buckets, and then we're going to iterate over every bucket, emptying each of them in FIFO order back into our original array. So that FIFO order is why we like to use linked lists, because linked lists implement that queue interface, queue being a FIFO data structure, and that makes this process a lot easier. Remember, since we are only iterating over all of the numbers twice during each iteration, and we're doing a total of k iterations, we have that O of k times n efficiency. Remember, k is not a constant, it is a feature of our input. We cannot drop it in this big O, we have to keep it there. There's a difference between sorting 100 5-digit numbers and 100 700-digit numbers. Those are very different uses of Radix Sort. It's an out-of-place algorithm because we're creating all these buckets. It's a stable sort. Remember, Radix Sort only even remotely works because it's stable, and it is not adaptable. Give you guys a little bit longer to finish writing this down or take a picture, and then we'll go on to Quicksort, which is the last sorting algorithm that we talked about. If some of you guys watched lecture, you'll know we talked about the quick select algorithm a little bit too. That's not on your homework, so I'm not really going to talk about it in Recitation. We should have some resources about that online. Overall, it's very similar to Quicksort, though, and if you wanted to learn it on your own, that would be fine. Alright, hopefully that's good enough. Last but certainly not least is Quicksort. Another algorithm that is kind of seems like black magic the first time you see it. Definitely did to me. It took me a long time to actually understand how Quicksort worked. So you're definitely not alone if you're in that camp. It's based on this algorithm that we call that is generally called partition. How partition works is we take some arbitrary element in the array, and we're going to split the array into everything that's less than it and everything that's greater than it. And remember, what that does is that will determine the exact correct place for the chosen element. Quick select will not be on the exam. You'll see that on the topic list, but we're not going to ask about it. That will determine the exact correct place for the chosen element, which is super cool. Because you can imagine, just with nothing else, if you call partition on every single element of the array, and it determines the correct place for each of those elements, the array is sorted. So that's really cool. So the question now is, how do we do this partition algorithm in a good manner? So, Quicksort, how it works is we just keep randomly picking elements and using the partition algorithm on them. How it works is we call the element that we picked our pivot, and we swap it to the front of the subarray we're currently working on. Then we initialize these I and j pointers. I starts to the right of the pivot, j starts at the end of the subarray. I is going to move to try to find anything larger than the pivot, because remember, large things should be on the right side of the array, but I is on the left. And j is going to start at the right side and keep moving left until we find something smaller than the pivot, because remember, small things should be on the left side of the array, but j is on the right side. So if they ever find any of those two elements and stop, then they're going to swap those two elements with each other. We swap array I and array j, then I moves forward by 1 and j moves down by 1, and we repeat this whole process. Now, when I say repeat this process, obviously I and j don't restart, they continue where they were. So I wanted to write that note here just for completeness. But one important detail is I and j crossing is also a stopping condition. So I added that to both of here. I know I was missing that last week, but that is important. If we cross j, or if j crosses I during this movement, we automatically stop. We have to be careful not to continue doing comparisons if I and j cross in the middle of what we're doing. Once I and j do cross, what we do is we swap the pivot with array at j. That's where the correct position for our pivot is in our array. And then we'll recurse on the left and right subarrays. So the left and right subarrays being everything left of our pivot after we've swapped it, and everything to the right of the pivot after we've swapped it. Because those are the elements all smaller than the pivot and the elements all bigger than the pivot. So they're kind of their whole mini arrays. And once we've sorted both of them, our entire array as a whole will be sorted. And remember, we get some advantage out of this because once we've got down to like size 1 subarrays, we're done. We don't need to do any extra work on them. We can even write a base case for size 2 subarrays to specially handle and say like, oh, if I get base case 2, then I just check and swap them or something. Or you can use the quicksort algorithm on a size 2 subarray. Both work. But you can probably see for efficiencies. So remember we said that Quicksort has this best case and average n log n and worst case n squared. This worst case of n squared, you can see this on the viz tool too, there's an option for it. If you always select the smallest element or the largest element as the pivot, then it basically becomes an instance of selection sort, where you're comparing every single element in the array to see if it's smaller than the pivot, which it's not, and then just swapping the pivot with itself at the beginning of the array, or with the last element swapping it to the end every time. So this worst case of n squared should be really easy to see. This best case of n log n, this happens if we select the median of the array every time. So if you consider the fact that partitioning takes O of n time, where n is the length of our subarray, and then if we split the array exactly in half and continue working on it, you should probably be able to see why the best case of quicksort is n log n. The argument is going to look very similar to what we did for the merge sort time efficiency. We're not going to ask you to derive this or anything, but it's important. And you should be able to kind of work through that on your own. The average case of quicksort is a little bit harder to do. You'll actually be proving this in a different class in CS3510 or 3511. They usually do it as one of the earlier on assignments. So this one's kind of difficult to show. These two are pretty easy, and you should be able to kind of work through these on your own. Don't worry if you're confused about the average case. A different way to think about it is that on average, we usually pick a good pivot out of 2 iterations. So every 2 iterations, we've probably picked a good pivot, and that gives us some good bounds on our efficiency. This worst case is really unlikely. It's actually like 1 in 1 over n factorial times. So even like with a size 5 array, that's like 1/120 chance that you get this worst case efficiency. A little bit more likely than that, but you get the point that it's really unlikely to get this worst case efficiency with large arrays. We usually get an n log n case. Remember, Quicksort is an in-place algorithm. We have these subarrays here, but they're actually just portions of our bigger array. We're not creating any new arrays here. It's an unstable algorithm because we're making these really long swaps without regards to any of the elements in between, and it's not adaptable. None of these last 3 sorts get any kind of improvements by starting with already sorted stuff or near already sorted stuff. I'll give people some more time to write this down or take a picture of it because there's a lot on this page. Some things written a little bit differently from how I did last week, even though we don't really have a lot of new information. But after this, we're going to do our introduction into pattern matching and talk about our first algorithm before we cut things relatively short today. So people have brought up some good points. When I say like the smallest or largest element for each pivot, if you're selecting the second smallest or second largest, those are still pretty bad pivots, and you'll get something like close to O of n squared. Generally, for a good pivot, we consider it something within the middle half of the array, if assuming it was sorted. So somewhere in between that like first quartile and third quartile, that would be considered like a good pivot. And considering that's half of our array, that's why I mentioned like out of 2 pivot selections, we're probably going to get a good one. I'll talk a little bit about quick select. Honestly, I can talk about quick select now. Basically, the idea with quick select is I'm not going to like write a ton of stuff down because it's not really something you super need to know, and the algorithm itself is super intuitive if you understand Quicksort. Basically, the concept is we want to know what is at some particular index in our sorted array. So what that means is someone might say, okay, given this array, what's the third largest element? What is the element that would be at index 2 if the array was sorted? Those are the same question. And you'll remember that this partition algorithm takes an element and determines exactly where that element would be if the array was sorted. So what we can keep doing is we keep calling our partition algorithm to determine taking random pivots, determining where they belong. But instead of sorting the array and calling it on both sides, we're only going to call our algorithm on one side of the array, whichever side we need to. So if we're looking for the element that's supposed to be at index 2, and we determine the element that's supposed to be at index 4, we're only going to recursively call our quick select algorithm on that left side. So the actual algorithm is only getting called on one side. So overall, we get a lot less work than Quicksort because we're not trying to sort the array, we're trying to do less than that. So we get something that's pretty good, But the actual algorithm and how we're doing the work is exactly the same as Quicksort. The only difference is we're not calling it recursively on both sides of the array. I encourage you to look at some of the course resources we have if you want to see a bit more about that, but the actual algorithm is pretty much the same. And it's got basically the same thing where the best case of O of n for quick select is really easy to prove, as is the worst case of O of n squared, but that average case of O of n is difficult for you guys to prove at the moment. So there's nothing really new to talk about with quick select, it's only stuff you've seen before. With that said, let's go ahead and move on to pattern matching. This is the focus of homework 9, and it's going to be the next algorithm that we talk about in this class, or the next class of algorithms. So what is pattern matching? Sometimes you also might see it get called string searching. I believe the Sai Krishna slides call it string searching. This is also the last things that we have Sai Krishna slides about. I think there's some other slides we've made about graphs, but dynamic programming do not have Sai Krishna slides or something like that. But they're not that bad. What it is we have some text. We say that that text has length n, so that's just the definition of n. Our text is usually long, and then we have a pattern of length m that is usually short. Now, this is short in comparison to the text length. And what we want to see is we want to know where the pattern is located inside of the text. We might be interested in only knowing the first occurrence, so the first time the pattern shows up, or we might be interested in knowing all occurrences, so every single place the pattern shows up. And you can think about this as just something as simple as like Control F on any web page or on like your code to find something. So if I was also searching for like, okay, where does the word of appear on this page? If I was looking for the first occurrence, I'd say, okay, right here. This is the first occurrence of the word of. If I was looking for all occurrences, then I'd get a little more. I'd say, okay, there's one here, 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 so on and so forth. So these are what we're trying to do. So you might think like, okay, I'm looking through a book to find where a character's name appears. So a book has a really long length. It's a lot of characters in a book versus someone's name is a relatively short thing. So n is usually much larger than m. That's what this means. This means like much bigger. So m tends to be insignificant compared to n in terms of length. And you'll see a little bit on about how that matters in terms of efficiency sometimes, but this is usually. So not always, but usually this is the kind of problem domain we're dealing with. What that means is for big O's, if we can get big O's that deal with m more than they deal with n, that's something better. So, if I told you to implement an algorithm to solve this problem, the one that you would probably write on your own is what we call the brute force the brute force algorithm. This is the most basic sort, no optimizations. You'll see next week we'll talk about a lot of really cool optimizations that people have come up with to make these algorithms really cool. But brute force is super basic, doesn't do anything fancy. How it works is we start by lining up index 0 of the pattern and index 0 of the text. And then one by one, we're just going to compare every single character in the pattern with our text. If we ever encounter a mismatch, then we just shift our pattern. Over by one and try again. We start comparing one by one with the characters that are lined up. You'll see that a bit when I do an example on the next page. A bit of conventions and just things for how I'm going to generally be talking about these algorithms and how you'll usually see them in notes is I refers to a pointer to the character in our text. So it's usually where the alignment starts between the text and the pattern. So when we're shifting the pattern, that's going to involve I moving. J is going to be the pointer to a character in our pattern. So as we're checking different characters in our pattern, J is going to move. And as we're moving our pattern, I is going to move. So I is generally something between 0 and the end of our text. J is something between 0 and the end of our pattern. Now, we've got these three conditions we need to define. What we're going to be doing is we compare text at... Let me draw a line here. These are separate. What this means with these conventions is that we are comparing text indexed at I plus j. I know you aren't actually allowed to index strings like this, but this is usually how we write it, just for the sake of convenience. It's going to be like text.char at. So it's actually like text.at I plus j. That's what this really is, but this is much easier to write. So we're comparing text at I plus j to pattern at j. That's how this convention kind of works, and you'll see that on the next page. When we've got these three conditions, we've got what happens if two characters match, what happens if two characters mismatch, and what happens if we get a complete match. So two characters match and it's the very end of our pattern. We've found a match. If a character matches, we're just going to increment j by 1. So this will involve us checking the next character of our text with the next character of our pattern, which is exactly what you expect. If we get a mismatch, we're going to increment I by 1. Remember, this indicates us shifting our pattern over by 1, and we reset j to 0 to indicate us going back to the start of our pattern. If we get a complete match, we're going to do the same thing. We're just going to move our pattern forward by 1 and start comparing again. This assumes that we're looking for all occurrences. Obviously, if we're looking for only one occurrence and we get a complete match, we just return I. That's the index that we found the match at, and then we're done. If we're looking for all occurrences, then we just store I in some kind of list, and we need to keep going somehow. So I'll give people a little bit longer to write stuff down because there's a lot of new stuff here. People, I'm sure, want to write it down or take a picture of it. And the next page is going to be just an example and talking a little bit about the efficiency of brute force. Spoiler alert, it sucks. And then that will be all the stuff I have for you today. So it's a pretty short recitation because we're trying to not get super far ahead of where the course is, so we actually finish on a reasonable schedule instead of a week and a half, over a week early. Alright, that's probably been plenty of time. Haven't been that many questions recently. A couple things that TAs have been answering. Thank you to those TAs. Big help. Some questions about regex and those differences. A lot of that's out of the scope of this specific course, but I encourage you to look up more stuff on your own if you're curious. But let's go ahead and get to this example. It's spooky season, so we're going to be searching for a ghost in our text. I'll give people a little bit of time to write this down. I'll move this page up once we get to the efficiency stuff. But to just write down this text string, this is the text we're going to be searching through, and we're going to be looking for the word ghost. You'll notice I've started with the text aligned up at index 0 of the pattern. So this is I equals 0. That should be a lowercase I. This is I equals 0. And j is going to be moving on. I'll give people some time to write this down so that they can kind of work through the example with me instead of having to scramble to catch up after I've already started. You obviously don't need to draw this fancy grid if you don't want to, but it's going to make it a lot easier to see what's going on from a teaching perspective. But your notes might not need it if you can draw the lines pretty well. All right, so let's start doing these comparisons. So I'll explain my convention as I work through this for how I indicate things, but the basic idea is when I do a comparison between two characters, I'm going to circle here in the pattern where that comparison happened. So that's going to kind of be a way to count the comparisons. You can just count the number of circles. So we compare this G to the G in the text. They match. So we increment J by 1. So now we have got J equals 1, I equals 0. So we're comparing index 1 to each other. That's a comparison. That's a match. Then we compare these characters, that's a match. Then we compare these characters, and that is going to be a mismatch. So I'll indicate that with this kind of circle with a line through it. That means I did a comparison, but I found a mismatch, versus just a circle as a comparison and a match. Writing it in a table like this means that you're always comparing with like the character in the text above it. So I'm not going to continue mentioning that from here. It should be pretty obvious. So remember what we said is when you get a mismatch in brute force, all you do is you shift the pattern down by 1. So this is like I equals 1. And we just start comparing again. So we start at the very beginning. We compare this G to the H. That is a mismatch, because G and H are not the same character. So we shift the pattern down by 1 again. This is like what if we have I equals 2. And we're going to start comparing again from the beginning of the pattern. That's comparing this G to this O. That's obviously a failed comparison. So now we can shift the pattern down again. And you can see that this is pretty bad. We're just doing these shifts by 1. We're not really making any kind of optimizations or any cool anything. Just brute force comparing character by character. This time we do get a match between these two G's, but then as soon as we get onto the H, that's a mismatch. So we shift our pattern down by 1 again. Compare this G to the O. That is a mismatch. So we shift down again. Compare the G to the B. That's obviously a mismatch. Then now we start comparing. G to the G is a match. HH is a match. O is a match. S is a match. T is a match, and we've successfully found an occurrence of our pattern. It's here at index 6. That's what this I is useful for. So if we're looking for one occurrence, we can just go ahead and return 6, because that's what we found. If we were going to look for all occurrences, we could try to shift this down by 1. You'll notice this T is kind of hanging over the bounds of our array, the bounds of our text. So because we've got pattern hanging past our text, it's not possible for us to have any kind of alignments here. So we can just stop immediately and say that the only occurrence was at this index 6. Anytime we never want to do any alignments that involve our pattern going past the edge of our text, because obviously it's impossible for those to be matches. I'll give people a couple more seconds to finish writing this down, make sure that what they've got in their notes matches what I've done. Then we'll talk about the efficiency of brute force, and that will cap things off for tonight. All right. I'm going to slide my page down a little bit. So, what is the worst? Generally, with these sorting algorithms, we like to talk about the worst case and the best case. Average is a really weird one, because these are based on our input of our text and pattern. So the average case is like saying, okay, what is an average text and pattern? And that doesn't really have a lot of meaning. So in this, you'll see that sometimes it's going to be really difficult for us to talk about the average case, and we're really only going to get one kind of just because it will either be there's really no other choice, or you'll see some examples later. But our worst case is really easy to look at. If we always mismatch on the last character of our pattern, so if we have a text that looks like this, and we have all A's, and if we've got a pattern that looks like this with a bunch of A's and a C, then you'll see we like compare this, compare this, compare this, compare this, compare this. Oops, that's wrong. Then we shift over by 1 and then compare, false. Oops, shift by 1, compare. And you're going to do that comparison for every single alignment. And that sucks. You'd think it would learn by now that something is clearly wrong if these comparisons are going on, but brute force is not a smart search. Brute force does not learn anything during the process of it trying to match these patterns. You'll see we do get something like that in our other algorithms. So because of that, we get this really bad case of O of m times n. So for every possible alignment, which is roughly n, we compare all m characters of the pattern. That's where this comes from. And you can imagine that brute force being as bad as it is, that's going to be what our average roughly turns out to as well, because these comparisons suck. We don't get any kind of efficiency from them. The best case is going to depend a lot on our problem. If we're looking for the first occurrence, you can imagine our best case is the trivial what happens if we just immediately find the occurrence we're looking for, O of m. That's going to really be true for any time we're talking about the best case of a searching algorithm. So we're not usually going to mention it for the other ones, but obviously if you immediately find your match that you're looking for, and you're only looking for one, then you're just going to terminate no of m time. But so this all occurrences best case, this is usually what we're talking about. Obviously look on a question what it's asking for, but this is usually the thing that comes up more. And the best case for all occurrences is going to be us mismatching on the first character of every time. So for this same text, if we have a pattern that looks like C-A-A-A, then on every single time we mismatch on this first C, shift by 1, we only do one character comparison every single time, and this is going to be O of n time. So people are asking about average case being like text that follows normal distribution of English language, but that's the problem. You're assuming it's coherent text and not gibberish. What if you're searching through code? That's not going to follow normal distribution of English language. What if you're searching through a DNA string for some specific sequence of nucleotides? That's not going to be a normal distribution of English language. So it really depends what is a normal text. Is it something from a book? Is it something from a code? Is it something from a web page? Is it something from a DNA string? There really isn't a good answer for that that's particularly satisfying. So that's why we really say that there isn't really an average case. And you'll see that when we talk about Boyer-Moore, that leads us to kind of the conclusion that you can't really give an average case of Boyer-Moore. KMP is a little easier just because it's obvious, but Boyer-Moore doesn't get anything like that. Brute force kind of does, because we just kind of say the algorithm sucks and call it MN in the average case. But we don't usually like talking about this average case. Just like with heaps, we don't ask about like average heap efficiencies. We're not going to talk about average pattern matching efficiencies very often. Regardless, I'll leave it open for questions and for writing stuff down for another minute or two. Then that will be all the content for this recitation. Did my sound just cut out? I stopped talking. I'm going to try to do a magic trick. I'll say that it's a trick I practiced a single time 2 weeks ago. I'll probably do the trick. Honestly, I'll probably do the trick and the tutorial for it, because I can't find the tutorial video for it. Alright, I think I've given enough time for people to write stuff down, and there haven't really been any questions that came up. So I think we'll go ahead and move on to that. That's all the content for today. So obviously if you have places to be that are important at 6 p.m., you can go there. Or if you have some kind of aversion to card tricks, which I did know someone that really didn't like card tricks because they had like some personal history with them that gave them bad memories and stuff. You obviously don't need to be here for this if you don't want to, but let's go ahead and do it with my cool green bicycle deck. I've got this deck because Target had packs of 2 in like a little metal tin on sale for like a couple bucks for like 2 decks and the metal tin, which was awesome. So I decided to get it. Something I'm going to mention, I've been hesitant to do this trick for a while because it does technically require audience participation. So I'm going to ask TAs to give me, in like the Slack thread, 2 numbers between like 10 and 20. I'll need them in a little bit, so hopefully by the time you hear this and give me those numbers, I'll be at that point in the trick. But the first thing I need to do for this trick is I need to pick out a couple of prediction cards. Otherwise, that's just an important part of this trick. So I'll go ahead and look through the deck and find those cards now. The first one of those cards is going to be the 3 of clubs. The second one of those cards is going to be the Queen of diamonds. And the third one of those cards is actually going to be a secret prediction. I'm not going to show it to you. I heard 2 Slack notifications. That's probably a good indication that I've got 2 numbers. Alright, so the 2 numbers I was given is Harrison gave me the number 14 and Harneet gave me the number 19. So those are the 2 numbers I will be using when I get to this trick. Obviously, I promise you that this trick would work with like an arbitrary spectator just normally telling me to stop. I'll kind of explain how that works. But I've got this deck right here. Let's go ahead and do like a couple of cuts to get started. And then what I'm going to do is I'm going to start dealing cards face down onto the table. And normally I would have a spectator tell me to stop at some point, but obviously I don't have that. So what I'm going to do is I'll use that first number and I'm going to deal down 14 cards. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Those are my 14 cards. And then I'll take this first prediction card, put it on top of this pile, put the rest of the cards on top of that, and that's that first part done. And we'll go ahead and give the deck a couple more cuts. And now we can move on to the next parts. This is where I'm going to do the exact same thing again. Obviously, I don't have a spectator, so I'll use the second number of 19, and that means I'm going to do 19 cards. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 cards. Take the second prediction card, put it on top, put the rest of the cards on top, and I can square up the stack. Now, let's go ahead and see what happens. If we actually look at these cards spread out a bit, you can see that we have these 2 points where the cards ended up. Now what I'm going to do is I'm going to separate that card with where the thing that ended up face to face with it. It's going to give me, try to keep all the stuff in the camera shot. That gives me this up here. Then we'll separate, we see this Queen of diamonds ended up over here. And the rest of the cards. So, they could have given me any number, a spectator could have told me any stopping point, but this 3 of clubs ended up exactly face to face with the 3 of spades, its perfect mate card. And the Queen of diamonds, again, another round, I could have gotten any number, you could have told me any stopping point, but you just so happened to stop me face to face with the Queen of hearts, its perfect mate card. Now you're probably wondering, we had these 2 stopping points, but I had these 3 prediction cards, so what's this third card? Well, this card just so happens to be the Ace of Spades, and that doesn't seem so obviously apparent until you realize that if we flip these piles over, then we've got all 4 aces right here. And that's just some magic, and that's going to be the trick. So now, let's explain exactly what went on and how this trick was done. So, these 2 prediction cards, the Queen of diamonds, 3 of clubs, or these 3 prediction cards, you can do whatever you want for these 2 cards. You can do something other than the 4 aces if you want, but the 4 aces are kind of the usual one, and picking the Ace of Spades as the prediction works pretty well. But these can be whatever you want. You'll just need the corresponding mate cards for them ready, along with the 3 aces. This is a trick that requires having the deck set up beforehand. What you'll want is you'll want these 2 mate cards sandwiched in between the aces like so, where you've got a first ace, the mate to your first prediction card, the second ace, the mate to your second prediction card, and then the third ace. You can put the aces there like that. It doesn't make that big of a difference. it'll kind of determine how the aces go. And you'll need all these cards starting out in that order on the bottom of your deck. Like this. Then what you do is you look through the deck, you pick out your first prediction card, you pick out your second prediction card, and you pick out your third ace card, which is going to go face down usually, to bring a little more suspense. Now, this trick mainly involves a technique in sleight of hand called a double undercut. What that does is it allows you to take certain cards and move them from the bottom of the deck to the top of the deck. So what we need to do now, the first step is to move the bottom 3 cards from the bottom of the deck to the top of the deck. So what I do is I peel off 3 cards, so with my thumb, just counting out 1, 2, 3 cards. Then I can readjust my hand to get a break like that. Then how I do the cut is I can use my index finger to grab about half the deck, push it out to the side, grab it in between the thumb and index finger of my left hand, move that to the bottom of the pile. At this point, the spectator isn't ever seeing this break. And I move it to the bottom of the pile, grabbing it so that those cards are now on top. Now you want to try to hide the fact that you're now just going to cut the rest of the cards to the bottom of it. You can do this in 2 cuts or 1. Then you take the rest of the cards, put them out to the side, and put them to the bottom of it. So this did not change the order of anything except those 3 cards, which have now been moved to the top of the deck. And you notice this has put the 3 of spades on the bottom of the deck. So now when you start dealing things out, you'll deal that ace down first, then your queen of hearts, then your other ace. Now it's important that you get these 3 cards dealt down, so don't let like a spectator tell you stop. Generally, how you can avoid that is you start dealing down, and then while you're dealing, you say, okay, now you can say stop whenever you want. And by the time you get to that point, you're already like 5 cards in. They can go for a while. Some spectator will tell you to say, or will say stop. You'll take the first card, put it there. Notice that we've got that 3 of spades on the bottom of the deck right now with this ace below it. So, because remember, what matters is what ends up face to face with it. So it doesn't care at all how many cards you deal down, because you're putting this pile on top of it, and that's what's going to make these cards match up. So now, what we need is we want this queen of hearts to be the thing on the bottom, so we're going to do another double undercut, but with only 1 card this time. So you can use your thumb to just peel off 1 card. Same technique, you cut a stack over, grab this 1 card on top of it, then cut the rest of the cards beneath it. So all we've done is take that bottom card and move it up to the top. Now you're going to do the same thing. Generally, you'll want to go for a bit just to make the cards spread out a little bit more, but eventually a spectator will say stop. You'll put the second card on top. Put this on here. Obviously, don't show them that that's where the card is, otherwise they'll realize what's going on. And then at this point, the trick is done. The important thing is just to spread out the cards to make these splits where the card ends up face to face. So that gets this first split here. The 3 and its pair. Second split, queen and its pair. Third split. And then you do the reveal. You show that this ended up with the 3 of spades. This ended up with the queen of diamonds. Show off that ace of spades. Now the important thing is, this is like differences between some tricks, is you're not flipping over 1 card here, you're flipping over each entire stack. So you flip over this entire stack to show the ace of clubs, this entire stack to show the ace of hearts, and this entire stack to show the ace of diamonds. And that's how the trick is performed. Super easy trick to do if you have an opportunity to prepare your deck beforehand. Obviously not an impromptu trick you could do if someone just like handed you a deck of cards and said do a magic trick, but still a nice one nonetheless. And that's all I've got for Recitation today. I'll give it a little bit to catch up to the live, and then I'll go ahead and end things off. Thank you guys for coming.